gauge anomalies. And the way we're going to figure out which gauge theories have anomalies is through a very similar derivation to what we did yesterday by using the path integral. So what we're going to be interested in are theories where we have, for instance, some left-handed spinners coupled to some gauge fields. So, for instance, for gauge group SUN. So, for instance, the standard model, we have chiral fermions that are coupled, they live in different representations that are coupled to the gauge group. It turns out repeating the derivation for this simple theory is much harder than by starting with a more complicated theory, which we can then simplify after we've after we've calculated the anomaly and reduce it back to theories like this, where we've got some fermions, perhaps chiral, that couple to a gauge field. So we're going to consider a more complicated model that will simplify our derivation. The reason it will simplify our derivation is because it will, the more complicated theory will map very closely onto what we did yesterday. So we're going to instead consider a theory with a fermion living in some representation, but we're going to change the gauge group and so what we're going to do is we're going to consider basically two gauge fields. One is coupled in a vector-like way to the fermion, and a second one that is coupled in an axial way to the fermion. So this theory has a SUN vector cross SUN axial symmetry. Don't often run across theories like this, but at the end of our calculation, we can set either the vector, either v mu or a mu to 0, and derive the anomaly if we only have a gauge field that's coupled in a vector-like way to fermions or in an axial way to fermions. And this theory is equivalent to, we can just rewrite this by defining left and right-handed fermions. Where I've defined d/L and d/R. So these are not defined using projection operators. Instead, this is just the way in which the covariant derivative couples to left and right-handed fermions. So d/L and R is just the ordinary derivative slash plus a/LR, where a/LR is v/ plus or minus a/. So there's no projection operators in either of these. In the definition, it's just how the covariant derivative, which covariant derivatives you should use for left or right-handed fermions. So, this first simpler theory is what we're interested in. And this will be simplify the derivation. So we'll consider this theory for most of the lecture and go back to a simpler theory where we just have, say, a single gauge group later on. Okay. So this theory has a chiral symmetry. Which has precisely the same anomaly we saw yesterday. So even though this is a non-abelian gauge theory, it still has an abelian anomaly. So what's meant by the non-abelian anomaly is this theory has another symmetry where we throw some generators in the exponential. And that's a classical symmetry of this theory, but it has a quantum anomaly. So this is also invariant. Under psi goes to e to the beta I of x, pi gamma 5 psi, which we can define to be u psi, and a goes to u, a mu, u inverse plus u inverse, e mu, u. So again, we're going to be working in Euclidean space, and although I'll probably mess up some of the minus signs, I'm going to try to use the conventions in Euclidean space where the generators are anti-Hermitian. And also the gamma matrices are anti-Hermitian, but gamma 5 is Hermitian. That's why there's no I here and no I's in any of my definitions of the covariant derivative up above. Although, stop me if I mess up a minus sign, an I, it's probably going to happen. Okay, so this symmetry has a global subgroup. So Noether's theorem tells us that there's a conserved current associated with this symmetry. And the conserved current is very similar to the axial current we have been studying for the past few lectures. The only difference is it has the generators. One of the generators in here. So as you can might expect, this is not gauge invariant. So this current is not observable by itself, which puts it on a somewhat different footing from the abelian axial current we've been studying. But nevertheless, it is covariantly conserved, classically. So that means that d mu ij of j5 mu j is 0. So what we're going to do is basically repeat the same path integral derivation we did yesterday. I'm going to go through it again, but mostly just to point out what changes. So most of the derivation will be the same, and the steps that are the same I'll go through a bit more quickly. But again, stop me if there's any questions. And one key subtlety that makes the non-abelian case different from the abelian case is that d slash is not Hermitian. So we can't find a complete set of eigenfunctions for d slash directly. And to see this, we can compute d slash dagger. So that's just gamma slash dagger plus d slash dagger plus gamma 5 dagger a slash dagger, which is gamma slash plus nu slash minus a slash gamma 5 is not the same as d slash. So we can't use d slash as a regulator in the same way we did before. However, we can use d slash d dagger slash and d slash dagger d slash. So these are Hermitian. Manifestly. So what we're going to do is, instead of using an eigenbasis of d slash, we'll introduce eigenbases of d slash d dagger slash and d dagger slash d slash. So we can introduce eigenbases, and the eigenvalues of d slash d dagger slash and d dagger slash d slash are the same. A, B, and BA have the same eigenvalues. So we can write the eigenfunctions as big phi and small phi, and they'll have the same eigenvalues, which will be, again, positive. So we can write this like this. And d slash will map small phi's to big phi's and vice versa. So there are two changes compared, two big changes compared to what we did yesterday. So the first is that instead of our symmetry just having a single generator, we now have a set of generators. which is a relatively minor change. But the more important change is that we need to use different bases for psi and psi bar. So you can write psi as an small phi n, and psi bar as a sum of phi dagger m of x b bar m. So those are the changes to keep in mind, and we'll see then what effect that has on our derivation of the anomaly. So yesterday what we looked at is how the action changes, and we saw that there was an extra term, and now this extra term looks like this. And the measure changed. So what we were computing was we wanted to compute the variation of the effective action for the gauge bosons. And after we'd done a chiral transformation on the path integral expression for the effective action. And so we do a chiral rotation on the measure. We pick up this inverse determinant, which in this case is exponential of beta gamma 5. And similarly for B bar. So then the variation of, so we had the effective action doesn't depend on is invariant. So this is equal to integral e psi bar e psi e to the minus s minus integral d4x minus integral d4x beta mu 5 minus 2 trace beta gamma 5. And so we can compute the anomaly just by computing this trace of beta gamma 5, just like yesterday. And because we want to introduce different bases for psi and psi bar, we can write the trace as two different terms. We have here 2 trace of beta gamma 5. Limit lambda goes to infinity. Integral d4 x sum of n by n dagger x beta of x gamma 5 by n, trace. Of x plus I dagger and of x, beta of x, gamma 5 by n of x.
And the regulator?
And the regulator, yes, that should be okay, either I need the regulator or no limit. So let's put in the regulator. Yes, throw that in here. Well, let's throw that in later. I had to introduce the regulator before. We can put it in. So that's f of minus lambda n squared over lambda squared. Thank you. Okay, and to save a little bit of writing, let's just define this as the integral of the abelian, the axial, non-abelian axial anomaly. And yesterday, it didn't matter so much what regulator we chose. Today, it's going to be useful to choose an explicit form of the regulator. So we can choose f of lambda minus lambda n squared over lambda squared, the exponential of minus lambda n squared over lambda squared. And we can use the same same procedure we used yesterday. To write this regulator, the eigenvalues in terms of these differential operators. But we have two different sets of eigenfunctions. So we should use the operator d slash dagger d slash on the small phi's and d slash dagger on the big phi's. And then the next step was to use our Fourier transform and use the completeness of the eigenfunctions. So that works in exactly the same way as yesterday. And if we do that, then we get that AA limit lambda goes to infinity, integral d4k 2 pi to the fourth, trace of beta minus ik dot x, gamma 5, e to the minus slash dagger, d slash, plus, same thing with the operators in the other order. Okay. So it's starting to look like we just have two copies of what we had yesterday. So these we had a very similar expression yesterday where if we just replace d slash dagger with d slash, we'd have exactly the same expression apart from the generators contained in the beta. And with a little bit of work, and we can put it in a form that's even closer. So to do that, we can go to a chiral basis. And rewrite d slash and d dagger slash in terms of the dl and dr I defined beginning of lecture. So d dagger slash dl, d slash is d slash l squared pl plus dr squared dr. D slash d dagger slash is the same thing with the projection operator switched. So you can show this just by using the definitions of dl and dr that was at the bottom of the top board up there. And remember, dl and dr are just the covariant derivatives that sit between psi L bar and psi R for dl, and psi R bar and psi R for dr. So they do not contain projection operators, and this is not zero. And straightforward to show that if d slash dagger d slash takes this form, then the exponential of d slash dagger d slash is pl e to the d slash l squared plus br e to the d slash r squared. This basically just comes from the fact that the PLs are projection operators. So if we exponentiate this, we just exponentiate each of these separately. And similarly, the exponential of the operators to the dagger in the other place is we just switch the projection operator. So what do we see? So we plug this in here. What we'll see is that the left and right-handed components give separate contributions to the anomaly, and the contribution of each is the same. So the same as the abelian anomaly. We just have beta instead of a theta at the trivial change. So this tells us that AA is limit lambda goes to infinity, integral d4k 2 pi to the fourth trace beta minus ik x So the left and the right give independent contributions to the anomaly, and both are the same as the abelian anomaly. So from here, we can basically recycle our results from yesterday. So the last few steps in our derivation were just basically Taylor expanding these exponentials, and then evaluating the integral. And that all works in exactly the same way as yesterday. So the net result then is that the anomaly is 1 over 32 pi squared, epsilon mu rho sigma, to trace beta, f mu nu L, f rho sigma L. What's the same for the right? And this is proportional to trace over a particular combination of the generators of the representation of our fermion. So it's proportional to the trace of TAL times the anticommutator of TBL with TCL, where TL is the generator of the representation of the left-handed part of the fermion, which in this case is the same as, for the theory we were just considering, the same as for the right, but we also have a similar contribution from the right-handed generators. And so it's the anti-commutator here just because of the epsilon here. If we exchange mu nu with rho sigma, that's an even permutation. So we have a here. So this is completely symmetric. It's manifestly symmetric under the exchange of the last two generators. But if we exchange the, we can use the cyclicity to see that it's completely symmetric. And so if these traces vanish, then it doesn't matter what the gauge field configurations are, the anomaly will always vanish. So if we want the anomaly to vanish, this is the trace we need to vanish. And one other comment is that for the non-abelian anomaly, there are some residual ambiguities in the regulation procedure. And if we, there are different ways we could regulate it, you would end up with slightly different expressions. Here we've derived what's called the covariant anomaly. The covariant anomaly is one of the two more important forms. The other one's the consistent anomaly. But both are proportional to the same trace. So if you look at some of the references on the wiki, you might see both forms mentioned. But the important part is that, for our purposes at least, is that both are proportional to the same trace. And the anomaly, regardless of precisely what regulator you use to derive it, is always proportional to these symmetrized traces. Any questions so far? Okay. So we started here by considering this non-abelian chiral symmetry. There's also a non-abelian vector symmetry. So we could have, at the beginning, started out by considering this symmetry, where psi goes to beta psi, where there's no gamma 5 there. And psi bar then would go to psi bar e to the minus beta. And so this symmetry is also anomalous. And the anomaly can be calculated in exactly the same way I just described. The only real difference is there's a sign that comes from sign difference that can be traced back to the sign difference here. And so this will lead to a vector anomaly, which is exactly the same, except it's left minus right instead of left plus right. And so we can use these results then to find the anomaly if we're just interested in a theory with a single gauge symmetry, like the very first theory I wrote down at the beginning of lecture, where we just have a left-handed fermion. And so we can use these results and then just set the other gauge field to 0. So for instance, if we're just interested in a single left-handed field, we can set A right to 0. And that will set then F right to 0. And we can use these results then to find the anomaly if we just have a single gauge group that couples in a chiral way or a vector or axial way. So we've seen that, so yesterday I argued that if we have a gauge anomaly, like this non-abelian anomaly we've just calculated, it ruins gauge invariance and hence renormalizability and unitarity. So we'd like these anomalies to vanish in order to have a consistent theory. So for the last part of the lecture, we're going to look at what restrictions demanding that the theory is anomaly-free places on the matter content. So that's the question we're going to ask last part of the lecture. When do the anomalies cancel? So we want ABC, which defined to be the trace, BA, BB, BC, to be 0. So we'll just consider a gauge boson that couples in a vector-like way for now. So that means we want the trace over all of the left-handed fermions minus the trace over the generators of all the representations of the right-handed fermions to be 0.
This is just to cancel the vector anomaly, right?
Yes. So typically, usually if we write down the fermionic part of a theory, we just write down a term like this with no explicit gamma 5. So that's the most common way to write things down. So we'll just focus on that case for now. But often, we might consider a theory that has left and right-handed fermions that live in different representations. Like, for instance, the Standard Model is a famous example of a non-abelian gauge theory with chiral fermions. So, we want to ask, is that non-abelian gauge theory, or under what constraints does the consistency of the non-abelian gauge theory place on the matter content of our theory? Okay. So there are several possible ways this can vanish, and they're not all independent, but I'm going to present several different ways that are somewhat related. And there should be one very simple way that should be very apparent to you just by looking at this formula, that these can cancel. Anyone give me an example? What if the,
No. I mean, we can't take them to be have the same form.
we could. That's,
Oh.
yes.
Oh,
So
okay.
that's the simplest possible case. We could take TL to be equal to TR. So that's one way. And so if the left-handed fermions live in the same representations as the right-handed fermions, then of course that cancels trivially. And in fact, it cancels even if TL is related to TR by conjugation by some unitary matrix. So if U is 1, that's the example where they're in the same representation. But if they're related by this formula, they live in equivalent representations. So here the left and right live in equivalent representations. And so by the cyclicity of the trace, all these U's will just cancel out. And so the cancellation will be the same as if U is 1. So that's one way. So anomalies are, that tells us anomalies are only potentially an issue if we have chiral fermions, left and right-handed fermions living in different representations. But clearly, it's not always a problem in that case, because we have the standard model, left and right-handed fermions living in different representations, inequivalent representations, but still a consistent theory. So a second way the anomalies can cancel is if all the fermions live in real or pseudo-real representations. So a pseudo-real representation is a representation where the transpose of the generator is minus V times TL times V inverse, or V unitary. So this is pseudo-real. And it's real if V is 1. And so we can see that this, for a real or pseudo-real representation, the contribution, any fermion in a pseudo-real representation doesn't contribute to the anomaly. So if all the fermions are in real or pseudo-real representations, there's no anomaly. Or if we have some fermions in a pseudo-real representations, we only have to worry about the other ones. They can vanish for one of the other reasons. And to see this, we can look at this trace. And so if we just, the trace of a matrix is the trace of the transpose of a matrix. So that gives us, we transpose it, we can then cycle things back into the same order. And we get this. And if it's pseudo-real, then we get 3 minus signs. 3 minus signs and the v's and v inverses will all cancel off. So we get this is equal to minus race PA PB PC. So that means this trace has to be 0. And most of the simple Lie groups only have real and pseudo-real representations. So SU2, SO2n plus 1 for n greater than or equal to 1, SO4n n greater than or equal to 2, SP2n for n greater than or equal to 3, as well as G2, F4, most of the exceptional groups. Also, all these groups only have pseudo-real representations. Or real representation. As do any direct products of these groups. Third way, or that anomalies can cancel, or we can disregard some fermions in computing the anomaly, is we have massive fermions. So massive fermions do not contribute. And so one way to see this is we can always rewrite right-handed chiral fermions in terms of left-handed chiral fermions. And so we could write a Dirac fermion entirely in terms of left-handed fermions. So and we do that. It's in my notes, but I don't think I'll have time to go through it now. We can show that. So if we rewrite left a Dirac fermion as two left-handed fermions, then we can think of this as a fermion transforming in a real representation. So this tells us that Dirac fermion, think of it as a lives in a real rep. And That just comes about because when we rewrite the right-handed part of the Dirac fermion as a left-handed fermion, that involves transposition. So we'll get a real representation like that. And similarly, massive Majorana fermions always live in real representation. So it's also possible that this trace can just vanish because there are no representations of a particular Lie group that have a non-vanishing trace. So even though SO for n plus 2 for n greater than 1 and E6 have representations that are not pseudo-real. They have no representations that contribute to the anomaly.
So when you said that asking this trace to be 0, we will get conditions of the type of matter.
Yes.
It's basically all these list things we're doing. We're saying, okay, my matter can have this type of colors and this type of n, and in that case, I will
That's
be okay.
right. That's right. So, yeah, for this case, if your gauge group is E6, you can have any matter you like. Doesn't matter. Or SU2, if your gauge group is SU2, you can have any type of matter you like. Well, at least there'll be no perturbative anomaly of the type we've seen. But you notice I have not listed all of the gauge groups. There's one case left. So if our gauge group is SUN for n greater than 3, or U1, then we potentially have anomalies.
Sorry?
Then individual fermions will contribute to the anomaly. And so the last case is for SUN n greater than or 3 or equal to 3, or U1 for products involving these groups. We have to have the contributions cancel. And so in this case, anomaly cancellation puts non-trivial constraints on what type of matter we're allowed to include in our theory. And in particular, this includes the case of the standard model. Standard model is SU3 cross SU2 cross U1. So it's both SU3 and U1. subgroups. And the anomaly cancellation puts strong constraints on the representations that chiral fermions are allowed to live in. And as you'll show in tutorial tomorrow, for the standard model, this puts a lot of constraints on the matter, but they're all satisfied. And that potentially anomaly cancellation can constrain additional matter. If you want to extend the standard model, you have to make sure that the anomaly cancellation still works out. So, yeah, a bunch of non-trivial equations that relate the representations of each other that you'll discuss in tutorial tomorrow. So that's what I wanted to say about anomalies. So we've gone through and derived two very different types of anomalies. The different in their implications, although we saw the derivations were very similar. So we first discussed the abelian anomaly, which is an anomaly for a global symmetry. And there's nothing particularly wrong with a global symmetry being violated by quantum mechanics. It can lead to interesting effects. On the other hand, non-abelian anomalies are gauge anomalies. They're anomalies that can spoil gauge invariance and ruin our theories. And if we want to have a consistent theory with chiral fermions, a consistent non-abelian gauge theory with chiral fermions, that places some constraints on our matter. And so tomorrow we will move on to instantons and discuss non-perturbative effects that we can learn about through instantons, like tunneling and the theta vacua of non-abelian gauge theory. So in the very last lecture, we'll see there's some connections between the two topics, but we'll basically be changing gears quite a bit tomorrow. And just a reminder, tomorrow there are two lectures, one at 9 and one at usual time.